Hi, everybody, and welcome to Astronomy on Tap virtual edition. We're trying a new type of segment this week. This is going to be a trial run of sort of an interview podcast style conversation. And for our trial run, it's just going to be us co-organizers, and we're going to see how it goes. So we encourage you to give feedback and let us know if you like it or didn't like it. And also, it would be great if we could get a cool name for it, maybe like Astronomy on Chat or Astronomy, something clever. If you have any ideas, feel free to comment on them below or send us a message, and maybe we can use that for our upcoming sessions. So let's go ahead and get started. So Emma Kun is a co-organizer of Astronomy on Tap. You may recognize her, seen her at our events before.
Hi, everybody.
Hey. She holds the MTA Premium Postdoctoral Fellowship at Konkoly Observatory here in Budapest. She was previously a postdoc at University of Szeged, where she also got her PhD in 2017, right? Yes.
Right.
Okay, so well, thanks for being our first victim of the the interviews.
I'm happy to be the victim.
Yeah, well, it's nice to have somebody involved that's also one of the organizers. So like, you can't blame me if it goes wrong, because it's also your fault, because it's everybody's fault. So to get started, why don't you just give us a brief overview of what kind of research it is that you do?
So I'm basically doing research on extragalactic astronomy, which means that we are dealing with objects outside of the galaxy, so outside of our galaxy, the Milky Way. I'm interested in the center of those galaxies. If the center of those galaxies is active, because the supermassive black hole at the very center of these galaxies is feeding on the matter about the black hole itself, the accretion disk will radiate light, and because of this extra radiation, it will be very bright.
Disk?
Sorry?
Can you explain what you mean by accretion disk?
Basically, it's an object in which the matter is orbiting toward the center or toward the horizon of the black hole.
Okay.
So the matter that goes too close to the black hole, it is not free falling, because of the momentum conservation, but rather it will spiraling in a disk.
Okay.
And in the disk, it is the matter is approaching the horizon of the black hole, and the whole thing will be very bright, and we can recognize those so-called active galactic nuclei very far from us. And because of this large energy, the immediate environment of the black hole will radiate high energy cosmic rays and neutrinos, and we are studying them.
Okay, and if you had to explain these active galactic nuclei and accretion disks to somebody that was 5 years old, how would you explain it to them? Like, just in like a couple sentences, like, how would you explain what that is? Wow. Not too much pressure, sorry.
just imagine a light bulb in your lamp. Okay. And the accretion itself, the process is like you are pushing a button to make it lighter. And if you push that button stronger and stronger, the bulb will be brighter and brighter. Mm-hmm. And if it is very bright, then you can bring this bulb far away from you and still see it. And this is the basic concept.
So what type of telescopes or facilities do you use to study these?
Radio astronomy.
Okay.
Because we are interested in the radio jets. Basically, those jets contain charged particles.
So like electrons, protons.
Okay. Yes. And because of the accretion disk, the magnetic field is generated, and then along the open magnetic field lines, charged particles will leave the system, and this is what we see as a jet.
Okay.
And it is radiating in many wavelengths, but it is radiating at radio frequencies as well, and we are using interferometric techniques to observe them.
So interferometry, so that's like where you have multiple telescopes working together as one big telescope, right?
Yes.
And so
yes.
what sort of advantage does that give you over just using a single telescope?
The resolution that can be achieved
Okay.
employing those interferometric arrays is very fine, much finer compared to using only one array, because if you are connecting radio interferometers, radio telescopes in interferometric mode, then not the diameter of the individual elements will be the important thing, rather the distance between them,
Okay.
the so-called baseline.
Okay.
And larger the baseline, better the resolution in that direction.
Okay. Cool.
So increasing the surface of the arrays, I mean the dish itself, will give you more dynamics. The array will be more sensitive, but the resolution is the one thing that is very important to us, to see the structure of the jets, how it is evolving in time.
So when you say how it's evolving in time, does that mean that when you observe these things, you can see things moving? Like you can see these jets shooting stuff out, or?
Yeah. You shoot one so-called picture. So the interferometer systems are not imaging systems, but you can do a picture from them. And if you took one, so if you observe the jet, and then after several months you are observing again and again and again, you are observing the jet across 10 years, you will see that the components of the surface brightness density of the jet will be changing. I mean, the components will be moving. Okay. And how they are moving, it tells us something about the base of the jet.
Cool. So are these jets, are these the kind of things that you have in every galaxy, or do they only happen around these active galaxies?
Only 10% of the galaxies are active. Oh, okay. And only 10% of those active galaxies have a jet, or a jet pair.
So then what about our Milky Way galaxy? Is it active, or does it have a jet?
No, it has a weak jet. Several years ago, astronomers used the Chandra, an X-ray space observatory, and maybe ALMA, I think, or really, no, ALMA. And they observed a very weak jet. Okay. Some of the activity of the central black hole of us, I mean, of the Milky Way, is increasing a bit. So using radio interferometric arrays, they have seen that the black hole is feeding on a very large cloud of gas and dust, and it causes a bit of activity. But rather it's not so hungry monster.
So do you think that maybe someday in the future it'll have a big strong jet, or maybe sometime in the past it had a big strong jet, or is it just different?
Wow, I don't know what is the correct answer for it. Probably it had, because there is a cycle of activity and non-activity in these galaxies. So for several 100,000 years, a galaxy can be active, and then other several 100,000 years it can be quiet, and then the whole thing is repeating itself. And maybe in the past, or the center of the Milky Way was more active. Maybe it will be more active in the next, who don't know in how many years.
So do we know what governs whether or not something's active or not? Is it just chance, or is it have something, you have to have something extra falling into the center, or what actually makes these cycles happen? Like, is it something that's like easily predictable? Like this one's not active now, but we know it will be in the future, or is it just like it will go along a cycle of accreting more material and having more jets, and that just happens to be like what gets close enough to fall into it, and that's just orbital dynamics, or
yes.
or is there some other fancy process going on?
For example, with the Very Large Array in Socorro, New Mexico, the resolution is not the best, but we see the kiloparsec structure of the active galactic nuclei with a very good sensitivity. So we can see quite weak remnant jets, so-called jets. So there are galaxies that are not active, so we do not see the very center of those galaxies with, for example, the Very Large Baseline Array, which is which gives much more resolution than the VLA. But with VLA, we see something in several kiloparsecs from the center. So very far from the center, we see some big remnant of the past activity.
Cool.
So for some galaxies, it can be suspected that they were active, but now not.
So, okay, so I want to switch gears a little bit to something that's a little bit more of a fun type of question. So, I want you to tell me one thing that you love about being an astrophysicist and one thing that you hate about being an astrophysicist. Because we know not every job is perfect and not every job is completely terrible. So, like, what is one, like, really thing that you really love about it and one thing that you really don't like about it?
I love it because it's very colorful. You can learn a lot. So in general, I'm a very curious person. So I want to know not everything, but as much as things I can incorporate in my mind. And I like so that you have to think about things that are several million light years away in the very past of the universe. And that's, I mean, it's very cool, I think. What I hate is sometimes it can be frustrating that you have to so you may heard that there is this constant push toward, so how to explain it, so there is a thing, publish or perish. So because we are on undiscovered paths, sometimes those paths can lead to not so nice results. I mean, contradictory results, or so something in some point something goes wrong, but still you have to publish something, show something. And we know the negative results are results as well, but not so shiny.
Right.
Than a new
So it can be frustrating. You feel like there's a lot of pressure to constantly publish, even if you don't have an exciting
I like to publish, so I really like it. I like to write, but sometimes it can be frustrating.
Okay. Yeah, I agree with that.
End of the year, and I still wrote just 1 or 2 papers, but I have to write 3.
Right.
Yeah.
Okay. So if you could have a dream telescope, like whatever telescope that you think would be the coolest possible telescope that has no price restrictions or anything like that, but is just physically possible. So don't say telescope the size of the galaxy, but or anything like that. Like, what would be your dream telescope that you would want to see built?
I'm dreaming of a very large interferometric array with quite good resolution and sensitivity to see the very center of the active galactic nuclei, what happens here. And yeah.
Do you think that
It
we'll
would be
like
nice to increase the resolution.
so bigger than the ones that we currently have, like longer
Yes,
baselines? Okay.
longer baselines. So it can be with arrays in space. It can be at least imagined.
Yeah.
There are some arrays in the space, but because there are just only one, two, or several arrays, the number of the directions along which the resolution is really good is very just a few baselines.
Mm-hmm.
So the beam, the so-called beam, is like a line.
So the beam is like the effective resolution.
Yes.
Okay. Cool.
It would be nice to have a rather circle-like beam with space antennas.
Cool. Yeah, that would be pretty cool. I support your dream. I would support that. Right. All right. Well, Emma, thanks for sitting down and chatting with me and being our first
Thank you very much.
guest on this new adventure that we're trying out with these interviews. So we're going to take a quick break and then we'll come right back.
Here's how you can make your own face covering in a few easy steps with items you can find around the house, like an old scarf, a bandana or a hand towel, or you can make a face covering out of an old t-shirt. Fold it to the middle from the bottom, fold it to the middle from the top, fold it again to the middle from the bottom, and again from the top, and then 2 rubber bands, one on one side and one on the other side. Then you fold either side to the middle and you have yourself cloth face covering. It's that easy.
So, hi Jacob, thank you for being here. You are a professional astronomer, and I learned that you are quite passionate about the public outreach as well. So
Yeah.
you are a very authentic person to do this interview because you are dealing with professional astronomy and public outreaches as well. So my first question, when you were a little boy, and if somebody asked you that, what will you be if you grow up? Did you have an answer that, or several answers, or the answer was depending on your age, or always you had know that I will be an astronomer and nothing else?
So I didn't actually decide to become an astronomer until I was already at university. So when I was a little boy, there was several things that or several big dream aspirations that I had. I remember from a young age, I wanted to be a pilot because I have some people in my family that are pilots. And so it just seemed like airplanes are cool. So it was like, oh yeah, I want to fly airplanes.
Fighter jet pilot or a commercial?
Well, fighter jet pilot. I don't have any fighter jet pilots in my family, but I mean, I thought it would be cool to be a fighter pilot, just because the big fast airplanes. Then my mom took me to the Johnson Space Center in Houston when I was maybe 10, 11 years old. And so after that, like I wanted to be an astronaut for a while. And then a little bit later, I wanted to be a musician or a rock star. I got really into playing guitar, and I thought for quite a few years that I was going to do something in music. That was what I was the most excited about. But then when I first went to university, I was studying business accounting. And I did that. I got a full degree in business before I switched and started studying physics and astronomy. So I actually came to the realization that I wanted to be an astronomer much later in my life. So
When you decided that, okay, I'm gonna be an astronomer, was there a picture in your mind what it's gonna be like, or did you hope that, okay, I will discover this, or I will have a Nobel Prize, or was there something big in your mind, or a
So
picture?
in my mind, when I decided that I wanted to do astrophysics in particular, as opposed to some other field of physics, I had in my mind that I would be doing a lot of physical observing, like going to the telescope and, you know, taking the data and then, you know, saving it and then taking it back with me and analyzing it. I don't think I've ever legitimately thought that I would do anything worthy of a Nobel Prize. But maybe I just don't dream big enough. But I mean, ironically, like, as I do a lot of, I do observational astronomy. I do with
Mhm.
radio telescopes, similar to what you do. But I've never actually used a telescope for scientific purposes.
Mhm.
Like I've looked through plenty of telescopes in my life, like small backyard telescopes and some larger ones at outreach events. But I've never actually taken data from a telescope in person because like all the telescopes that I've used have been the really big ones where they're expensive enough that they don't want me coming anywhere near it. And so they have people that they pay and it's their full-time job to operate the telescopes. And I just tell them what I want it to look at and what instruments to use. And then after they do it, then they send me the data and I can start doing the
It's
science
quite
on it.
different to what people have in mind when think of
Yes.
astronomers.
Yes.
I know you study circumstellar disks
Mhm.
of gas and dust around planet-forming stars. Can you tell us a bit more about this, what you are using?
Mhm.
Why is it important for science? What we can learn about your studies?
So circumstellar disks are, yeah, they're the, like you said, they're the clouds of gas and dust that orbit young stars.
Mhm.
So we think that probably most stars will have some sort of circumstellar disk in their evolution. Now, all of that material may fall onto the star or get blown away, so planets may not form. But we do know that planets do form at least sometimes because, I mean, I don't know about you given the background, but I'm on a planet right now. So we know that there are some planets and then we've seen planets elsewhere. But it's still an open
Okay.
question in terms of the exact formation processes. So we try to look at a whole bunch of different young systems at different stages of development to see how the planet formation process goes. Like, is it just like one physical mechanism? Is it a bunch of them? Does it depend on the stellar type? Does it depend on the abundance of certain molecules in the circumstellar disk
Mhm.
and things of that nature? So I particularly, or I most commonly use radio telescopes to study them. You can study
Okay.
it at almost any wavelength. I don't think there's any gamma ray protoplanetary disk studies, but I mean, if I say that, I'm probably wrong. So I didn't say
You are
that.
writing proposals.
So there's, but like, I mean, at optical wavelengths, like with the Hubble telescope, you can see some big fancy disks, like with the material swirling around. But at radio wavelengths, you can see some of the larger grains. You can see the thermal
Mhm.
emission from like the millimeter to centimeter sized grains. And these are the bigger grains that have to, they don't get that big naturally in these nebula before stars form. So these grains, we think that they have to form in the disks themselves. And then this abundance of these small, some people call them pebbles. So you can kind of get a visual
Mhm.
about how big they would be. These pebbles
Yeah.
form throughout the disk, and then those can go on to clump together and make bigger objects, which then go on to
Uh-huh.
make planets.
So if you
So
see the signal of those things, then, oh, there is a planet here, or there is a possibility to have planets there.
right. So we can't necessarily look at these pebbles and say, oh, there is a planet there, but we can look at where there could be a planet. So sometimes
Yes.
these smaller grains, they will kind of clump together at certain positions in the disk, and then that
Mhm.
position is based off of where a bigger planet could be. So sometimes it's as simple as like a protoplanet or something that's on its way to being a planet, sweeping through the disk and kind of collecting material as it goes, and you see a gap in the disk. And sometimes it's more like a ring. So if you think of like the asteroid belt in our solar system, it's just a whole bunch of asteroids that lie between the orbits of Mars and Jupiter. But if you were an alien observing us, you could look at those asteroids and see where they are and then make a prediction about where Jupiter is, because they lie at what's called an orbital resonance with Jupiter, which means that like there's certain intervals, which we call resonances, that stuff will congregate because of the gravitational interaction between the sun and Jupiter. And a lot of times this material will kind of fall into these resonances as well, and we can see where planets could be based off of that.
Okay, cool. That's very nice. Can you recommend us a paper, public outreach paper or something on that?
A public
Just
outreach
if somebody
paper.
is interested, then is there?
Yeah, so I can provide a link to a paper when we put this online. So the National Radio Astronomy Observatory in the US, the NRAO, has a really good public outreach program, and they have some cool visuals and videos about the planet formation and circumstellar disk processes that you can see with radio telescopes. And I can put a link to that on here. I don't have one off the top of my head that I could just say, go to www.coolspacestuff.com.
Name of associations or something like that.
Yeah.
Okay, so we are close to the finish. Is there a message from you to the young people who want to be an astronomer or a scientist?
Yeah. So if for people who say that they want to be an astronomer, I would say it's always good to have an open mind, because I, for a long time, didn't know what I wanted to do. So the whole thing of follow your dreams is obviously true, but it's important to know that dreams can change, and that's totally fine, because you don't know everything about the world when you're 10 years old, and you don't have everything laid out in front of you. I can do this, I can do this, I can do this. Oh, this one's the coolest. This is what I'm going to do. I mean, if that was the case for me, like I wouldn't be doing astronomy, because I wasn't really aware of it as a potential field when I was younger. But if you do want to go into astronomy or really any type of science, it's important to know math, and computers are very important as well. I mean, most of what I do is computer programming of some sort these days. But you don't have to be a math genius. It's okay. The biggest thing is that you want to do it and that you're passionate about it, because then you can figure out everything else on an as-needed basis. Like, I don't just like sit in front of a whiteboard and like derive equations and like have an aha moment where everything just comes to me. I'm not that great at math. I'm not that great at programming, but I figure it out as I need it, and I use it as I need it. So it is important to learn those things as you go and try to pick it up, but it's not important to be the best at it. You can still succeed and be a very successful astronomer and not be the smartest person in the room. I mean, just look at me. I'm usually the dumbest person in the room, and I've done okay. So
yes, I agree. Open mind is key.
Yes, it's okay to change your mind, and it's okay to not know what you want to do, for sure.
Okay, thank you for being with us. And
yeah, thanks for talking to me.
Bye-bye.
Bye.